Hello, and welcome to Astronomy 100. In a previous segment, we were talking about one of the more important partnerships in the history of astronomy during the time of the Renaissance. And what we talked about was Tycho Brahe, who was somebody who was a firm believer of the geocentric model, which doesn't help us in our understanding of the universe. The geocentric model was a very popular one in its day, and it was one that lasted for at least 1,500 years. But what we find is that Tycho Brahe was able to contribute very, very accurate observations of the nighttime sky, something that had not done, at least to that degree of accuracy, before Tycho. Tycho Brahe, towards the end of his career, is forced to leave Denmark, and he moves to Prague, Czechoslovakia, and is in need of some assistance to help him continue his observations. And in the year 1599, he hires the young Johannes Kepler to come work for him. Now, as I mentioned in the previous segment, Kepler was a mathematician. He was somebody who was interested in astronomy. He's from Germany. And he is somebody who is able to provide the assistance to Tycho that Tycho so desperately needs. In the year 1601, though, would be a really critical transition in the relationship between these two, because in 1601, Tycho Brahe dies an untimely death. And he does not die of old age. He dies from an illness, a very, very serious infection that would cause him to linger on his deathbed for a few days as he is essentially dying. And he summons Johannes Kepler to come to his bedside, and in his feverish fighting the illness that he has, he's able to ask Kepler to do him a favor, and that is to carry on his observations and to make some significance out of all of his observations that he's made about the nighttime sky. He's worried that he's going to die and take all of this with him, and the world will not know of what he's been able to measure and discover about the universe. So in 1601, Johannes Kepler inherits 20 years worth of very accurate observations made by Tycho Brahe at his castle at Uraniborg. And what he will do is, over the next 2 decades, he'll discover that there are actually 3 very basic laws that describe how planets orbit around the sun. And so, using the observations of Tycho Brahe, Kepler learns that there's mechanical means in which the planets, as they orbit around the sun, as they follow very specific rules that are governed by our universe. And so, in this particular segment, we're going to talk about Kepler's laws of planetary motion. And these laws, again, come from the observational data that started with Tycho Brahe. So let's talk about his first law. In the era of the Renaissance, it's believed that the universe is geocentric, that the Earth is the center of all things. But what's critical to know about Kepler is he comes from a perspective that the universe is heliocentric. And even though it is common to believe in the geocentric universe, Kepler strongly holds to this heliocentric idea. And so what Kepler is able to do is to take the data, the observational data of Tycho Brahe, and interpret it through the eyes, through the lens of heliocentrism. So let's look at his first thing that he accomplished. When the data, the observational measurements made of all of the stars and planets are put into an orbital or perspective of the universe that includes orbital movement, Kepler is able to show that by linking together the dates of these observations to various positions that the planets should be in their orbits around the sun, he's able to create orbital paths or orbital movements of the planets. And in this first one, what we have is a representation of the orbit of Mars. An example is an observation made in 1579 would be this dot right here, and then an observation made in July of 1580 would be this dot here, and then an observation made in November 1580 would be this dot here. So each of these dots represents the position of Mars in its orbit around the sun throughout the period of time that Tycho is making measurements of the sky. Now, Kepler believes that the universe follows very strict shapes and orders that are governed by the gods. And if you remember from a previous segment, the assumptions that were made about the shapes of the movements of objects and the shapes of the objects themselves, one of the assumptions that was made was that all movement was perfectly circular. And so Kepler applies this assumption, this idea that had been around since the time of Ptolemy. And what you can see quite clearly is that when you try to describe the movement of a planet around the sun, in this case Mars, by a perfect circle, you could see it does not fit very accurately. Many of the observational points that were made of Mars will fit, but then many of them do not. And so after a few weeks of working with this, Kepler realizes that there's no way that he can get a perfect circle to fit these observational points. And this assumption that all movement of the bodies of our universe are perfectly circular seems to be one that is just not right. And he tries to make the circle bigger, and it doesn't fit any of the points very well. If you push the circle to one side versus the other, it will fit some of the points, but not the others. And after a few months, Kepler realizes that this perfectly circular shape that he's trying to force to fit the observations of Mars just isn't going to work. And so, being the mathematician that he is, Kepler starts to explore alternatives to the perfect circle. And the one that he figures out is worth a try is one that he's troubled by because of its odd shape. But he's trying anything he can to fit a particular shape to the orbit of Mars. And when he does this, he tries the shape of the ellipse. And when he does this, he finds that it fits perfectly. So Kepler has discovered that the only shape in geometry that will fit all of the positions of Mars in its orbit around the sun is an ellipse. The ellipse is an odd shape. It's not quite round. It's really kind of a shape that has some strange features to it that Kepler just doesn't quite like. But he can't convince himself that any other shape is going to fit but this ellipse. Now, thinking that this is just something that is a feature of Mars and is strange about Mars as an individual planet, he decides to try the shape of the ellipse to the other planets. And what he finds is that the only shape that will fit the orbits of any of the planets is the shape of an ellipse. He even fits an ellipse to the orbit of the Earth. And he feels that he's discovered something about the universe that is sort of a rule of the universe, one of the laws of the universe. And today, in his honor, we refer to this as Kepler's first law. And let me show you the wording of Kepler's first law. Kepler's first law states that the orbit of a planet about the sun is an ellipse with the sun at one focus. And the use of the word focus there is something that many people are familiar with, but we're going to use it in a different way. This isn't the focus that you would have for a telescope or a magnifying glass or a pair of binoculars. The word focus comes from geometry. So let me show you what this means. Here is a perfect elliptical shape, and it is shown to you by the geometric features that make it the shape that it is. In geometry, there are two positions that are located inside of every ellipse that are part of describing the shape of the ellipse. And each one of these 2 points is called a focus. The plural is foci. So this is a focus, this is a focus, these are 2 foci. And what you can see is that this position and this position have a certain distance between them and a certain distance between each of them in the center of the ellipse. And it is the distances involved that will describe the actual shape of the ellipse itself. So what I'm going to do is 2 things. I'm going to show you what he means literally by his description, what we now call Kepler's first law. And then I'm going to show you how each focus plays an important part in the overall shape, and of course relate that to our solar system. So here we go. Here is what he's literally saying. He is saying that the orbit of a planet around the sun is the shape of an ellipse, and the sun occupies one focus. So if you remember from the previous slide, there are 2 foci inside of every ellipse, and he's simply saying that the sun occupies one of them. What occupies the other one doesn't really matter. There is nothing there. We're simply using the shapes from geometry to describe something realistic about our universe. Now, How does the position of each focus and determine the overall shape of the ellipse, and why is the sun at one focus? Let me show you how. One way to get this point across is to show you a more artistic way of describing an ellipse. Rather than using the mathematics and the formulas of geometry, let's do this artistically. If you've ever seen this trick done, it's quite nice. The way that it works is that if you want to draw a perfectly shaped ellipse, what you can do is start with a piece of cardboard, and then you put two thumbtacks at whatever distance you choose, and then you're going to use a piece of string, and you're going to loop the string on either end around each of the two thumbtacks. When you take your pencil and pull the string tight, what will happen is, as you let the string guide your pencil, the string will force you to draw a perfectly shaped ellipse. The reason why this is because the distance between the two thumbtacks and the length of the string is going to mathematically force the pencil to draw the shape of an ellipse. So each focus represents something about the overall shape of the ellipse itself. And what Kepler is saying is the sun occupies one of those two foci. So let me sort of show you how this idea works. Let's say we start with an ellipse with two foci at this distance you see here. And what I'm going to do is I'm going to take the distance between the two foci and we're going to pull them further apart. So essentially we're going to make the distance between the two foci larger, but we're going to keep the same piece of string, if you will, or the line will not change its size. So imagine doing this by pulling the two thumbtacks further apart, but keeping the same piece of string. What you end up getting is an ellipse with this shape. And so you'll notice that the distance between the two foci determines how elongated the ellipse is. And in the world of math, the elongated shape is what we call the eccentricity of the ellipse. When the two foci are further apart, the ellipse becomes more narrow. Now watch what happens when we take the two foci and we pull them closer together. And in this case, what I'm going to do is make the distance between the two foci 0. So imagine taking the two thumbtacks and putting them together at the same point, but use the same piece of string. And what you'll notice is the shape now becomes a circle. So in geometry, a circle is actually an ellipse. It's an ellipse where the distance between the two foci goes to 0. Now, turning this into Kepler's first law, what this means is the orbit of a planet around the sun is the shape of an ellipse, and the sun is at one focus. What this also means is that you can have a perfectly circular orbit, and what you would have is the object being orbited, in this case the sun, would be at the center of the circle. But if it is not a perfectly circular orbit, then the sun takes on the position of one of the two foci and is now off-centered. And if you remember from a previous segment when we talked about the seasons, we already revealed that the shape of the Earth's orbit is elliptical and the sun is actually off-center. And now what we have is a geometric explanation of specifically where the sun is and why it is where it is. So Kepler's first law describes the shape of the planet's orbits around the sun and the position of the sun inside of each of those orbits. One final thing I want to add to this concept of Kepler's first law is that this shape describes the orbits of all planets. So in our solar system, Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, they all have elliptical orbits. And what they have in common is the sun occupies one focus in each of their orbits, but it's the same focus in all of their orbits. So as Mercury orbits around the sun, as Venus orbits around the sun, as Earth orbits around the sun is at one focus for all orbits of all the planets in our solar system. Kepler doesn't know it at the time, but what he's actually discovered is one of the consequences of gravity. This is something that gravity does when it comes to orbital mechanics, or how something orbits around another body. You can have elliptical orbits, you can have circular orbits, but the geometry of the orbit of a planet going around the sun is ultimately governed by gravity. Unfortunately, Kepler wouldn't quite make that connection and understand that gravity is what's governing all of this. In the next segment, we're going to continue with Kepler's laws and describe how the observations of Tycho Brahe would lead Johannes Kepler to discover 2 more rules about planetary motion. I hope you'll join me.